the issue. Actually, it is not coming. So I press the third button, but it is not coming. Now I have pressed the third button. It's coming.
So now all the slides have been shown. If you can press the third one, sir.
I am saying, I have. What you do then? You can actually this video is playing, sir.
Asking to go to slideshow.
Is the video played?
So kindly, sir, if you go to the slideshow tab, sir, there is the slideshow menu. Sir, slideshow menu, sir, in the taskbar, sir.
I have done it, sir. Actually, I have done it, but it is not.
So now all the slides have been shown
in the bottom.
in small mini size version.
Again, I start presenting.
So if you go to the slideshow, it is view.
Ask him to stop sharing and start the sharing again.
Stop course. Okay. Hey, joining. Hey. সবাই জয়েন করে
बेगुन फुलिया तो सर it is sound
Hello?
Hello, am I audible? Lavani madam, am I audible?
Yes, ma'am.
Okay. Uh, Good afternoon, everyone. Welcome to day 3 of the Faculty Development Program on recent trends in renewable energy, organized by the IQAC cell of RERGI. I am Abhilasha Sao, Assistant Professor of Basic Science and Humanities Department, and with me is Mr. Sabyasachi Mukherjee, Assistant Professor of Mechanical Department. We are pleased to be your host for today's session. Attendance in all sessions is compulsory to qualify for the certification. Today, we have the privilege of hosting a distinguished academic and a researcher in the field of mechanical engineering, Dr. Shantanu Datta. Dr. Datta is currently serving as a professor of mechanical engineering department and a dean of research and academics at Shanaka Educational Trusts Group of Institutions, Durgapur. He has over 11 years of academic experience, having previously held significant positions at NSHM Knowledge Campus and Elite College of Engineering. Dr. Datta's industrial experience is equally remarkable, spanning over more than 14 years, with notable roles in the Ministry of Defense, Government of West Bengal Power and Chemical Department, and leading multinational corporations such as Siemens and TIL Kamarhati. He holds a PhD and a MTech in Mechanical Engineering from NIT Durgapur and a BTech from Jalpaiguri Government College of Engineering, along with a PGTM in Supply Chain and Materials Management from IIM Mumbai. A recipient of GRF and SRF scholarships, Dr. Datta has authored 51 publications in reputed journals and conferences and recently published 2 patents. His research contributions have earned him recognition in the World Scientist and University ranking by AD Scientific Index for 3 consecutive years. He is also a member of doctoral committee under MacAut and has conducted several national level FTPs. His Google Scholar citation count stands at 511 as May 2025. Today he will be speaking on the topic exploring solar energy, state of the art technologies, real world applications and research trajectories. Let's now welcome Dr. Shantanu Datta to take over the session. Sir, please.
Am I audible? Hello?
Yes, sir. Yes, sir, you are audible.
Acha. Okay. Okay, sir. Okay, ma'am. Thank you so much for giving a very big. I am basically a very small researcher in the domain of mechanical engineering, and basically I am very much honored that the RERF as a society has invited me to deliver a very nice FDP session. So I will be presenting some of the research work that I have done while I was there in Elite College of Engineering, and some of the research while I am presently serving as Dean Academic and Research in Sanoka Educational Trust. So my topic for today is exploring solar energy state-of-the-art technologies, real-world applications. So I have divided my presentation into 2 parts. Basically, the first part is the basic perspectives and future trends, and the second part is actually dedicated to my research. So without wasting any further time, I will move to my slides. So what is solar energy? So solar energy is the energy that we receive from the sun, and basically there are some questions which you need to ask before you start on the research of the solar energy. What makes your vehicle hot when it is parked in the sun? What makes your solar calculator work? What makes plant grow? Okay, along with the photosynthesis part. What makes the solar panels work on the roof of the solar? So if you basically deep delve into these particular aspects, then you will understand what is solar energy. So it is the energy that is coming from the sun. It is a very simple definition, and maybe in the school level, but that actually will give you more aspects, and you will actually be more delighted to research more on this particular fascinating subject, which is a very strong topic of the renewable energy. Now, how much solar energy that does we receive? So you will be astonished to know that we are actually receiving 174 petawatt amount of energy in particular 1 hour. You will be astonished to know that 1 petawatt is equal to 1 into 10 to the power 6 megawatts. Okay, and 89 petawatts of is absorbed by the land and oceans, and 10 petawatts, 35 is reflected by clouds, then partially 7 is reflected by Earth's surface, 111 is reflected by radiated to space from the atmosphere, and some is reflected by radiated from the Earth to space. Okay, and 89 petawatt is absorbed by the land and the oceans. Okay, and half the incoming solar energy, that is actually we are reaching the Earth's surface after penetrating the different particular layers, the troposphere, stratosphere, ionosphere, exosphere. Okay, so this is the amount of energy, energy that is receiving per hour. Okay, so this amount of energy we are receiving. Now, what are the different types of solar energy? Okay, so solar energy basically, I will be dealing with mainly. I will not be dealing with the very broad aspects, but mainly the solar energies are divided into three parts: the photovoltaics, the solar heating, and the concentrated solar power. So from the figures, you can actually basically understand the what is photovoltaics, solar heating, and concentrated solar power. The figures are self-explanatory. I will not waste much further time on this type of this slide. Okay. So now there are two basic categories of solar energy. Solar electric, which is your turning light from the sun directly into electricity using solar panels, and another is solar thermal, which is using the sun's energy to heat things like your house, their water, food, etc. So here in the figure you can see that basically it is a greenhouse type of arrangement. It is a glass house that we are receiving. On the top part also it is basically open, and you are receiving solar energy that is reflecting from the uh, this particular glass. Okay, and in the previous slide you have seen that that is the solar panel that is receiving the sun rays falling on the solar panel, and you can see that it is particularly inclined to some degree. So I will discuss all these things later. Okay, and from there it is gonna going to the inverter, and we are generating electricity. Now solar heating. So solar heating, as I told, is the process of harnessing the sun's energy to generate the heat for various applications such as water heating, space heating, right? And it does have many industrial processes. And this is the key component of solar photovoltaics, because that converts sunlight into electricity. So it is basically, you have to understand that it is a key component of solar thermal technology, which is differing from solar photovoltaics. And you should not get confused on the solar thermal and solar photovoltaics, and they are distinctly different. Now, the types of sizing building designed to naturally absorb and distribute heat without mechanical systems, maybe the south-facing windows and thermal mass materials like concrete, etc., which we are receiving and absorbing and distributing heat without mechanical systems, right? And another one is the active part. So this is using mechanical components such as fans, pumps, and it is basically used to circulate the heated air or fluids. Okay, and there are several thermal applications. Now this is the solar heating. As you can see, it is providing warmth to the buildings using air. It is also self-explanatory that solar is falling on the particular house, and cold water. Now we'll go to some statistics of this solar energy. So here you can see the percentage of solar energy adoption, right? So this is that China is having around 40 gigawatt of energy adoption for solar energy, and European Union has having around half of that. United States also, it comes to around 10, and India is actually lagging behind in this sense, because it is quite lesser compared to China, EU, or United States. But it is clearly it is picking up under the Modi government. It is quite picking up. It is fastly adopted. So all these values are in gigawatt, right? So that is not actually written, but yes, I have to tell that. So this is the solar map of India, where you can see that where actually you are receiving more of the energy. So on the Rajasthan part, on the western part, or maybe on the top part, Jammu and Kashmir. So here the kilowatt hour per square meter actually solar radiation is actually receiving, we are receiving more. So around 500 trillion kilowatt per energy is incident over in India's large area, with most parts receiving 4 to 7 kilowatt per square meter per day. So you imagine how much of solar energy we are receiving in India. Okay, so this is a basically collected from Terry website. So I have given, and it is basically it is in the month of May, June. Okay, in the solar, in the month of hot weather. India's renewable energy future. So we are having having around a target of 500 gigawatt of non-fossil fuel by 2030. The cost have decreased nearly 80%, which is very much encouraging. Okay, so they are also giving several incentives to several bodies also, so that we actually install more of a solar PV in the homes. And my research is also based on this solar PV. We'll discuss that later. So, okay, so this is the India's renewable energy growth. You can see it is gradually increasing. It is a very increasing trend. So I have put the solar, wind, hydro, and others. So even the major part, okay, the wind and hydro is also comparatively means quite high. But yes, obviously the hydro part is the highest over here. As you can see from 2025, the hydro part actually the green part is actually the highest. Okay, and the solar is actually the blue part. It is also comparatively quite. It is also comparatively quite, and it is comparative to hydro also. Okay, so you can see that there is a huge prospect of India's renewable energy growth. So from 2015 to 2025, so in the span of 10 years, India's renewable energy growth in solar and hydro has remarkably increased. So I should concentrate more on the solar part, because this is my talk is basically on the solar. Okay, so from the graph it is very much clear. This is the green, light green is the wind, the other green is the hydro, and this blue is the solar. Okay, and the remaining is the others, right? So the National Solar Mission is targeting around 100 gigawatt of solar installations by 2022, and the progress is also ongoing. And then there are green hydrogen missions, advancing energy shortage, storage, and hydrogen economy also. So this is also some policies which is also picking up. I will not actually waste much time, because this is not dedicated to solar. But yes, obviously, the first point is relevant. So we are targeting around 100 gigawatt of solar installations by 2022. And this is 2022 data, and now we are in 2025. So obviously, this figure has now increased to 120 or 125 gigawatts. Now, this is a state-wise energy installation. So, but it's unfortunate that we cannot see the West Bengal scenario. Yes, obviously, from the India's map or the geographical locations, it is quite clear. You can tell that yes, Rajasthan and Gujarat, obviously they will be having more solar energy installations, because we have the desert, the favorable conditions of more solar energy in those places, and if they are more hotter, okay, compared to the other states, right? So they are actually, it is the reason that we have more Telangana. Okay, so obviously West Bengal is not featuring in this compared to Rajasthan, Gujarat, or Karnataka. So that's why I have not put this particular data of West Bengal. Now, as you can see, the energy storage and grid integration trends. So battery storage, solar, and heat. This will we are by using some AI tools. Okay, here you can see that by 2030 to 2022. Okay, so the energy storage in 200. With more amount of population, we are now the most populous country of the world, and there is more amount of people. Scenario will actually go up, and government will most set up So this is the, you can see this is the renewable energy is around doing a lot of research, and this BTU means British Thermal Unit. So total is 90. So uh, 1 trillion, you know how much.
Requesting all the participants to be patient and please keep joining with us. There is a technical glitch at speaker side, so please be connected with us. He will be joining soon.
Hello, sir. Can you listen to me?
Yes, sir, you are audible, sir.
Hello.
Yes, sir, yes.
Hello,
Yes, sir, you are audible, sir. You are audible.
sir. Actually, can you share the slide? Then I can discuss.
Okay, sir.
Actually, no net is coming over here. Maybe some problem is there. Okay.
Okay, sir, give 1 minute, sir. 1 minute. We are sharing. We are sharing.
Ha. Okay, sir. Okay, sir.
Yeah,
Okay.
we are sharing, sir. We are sharing. 1 minute.
Okay. Okay. Okay, sir. So actually, move to slide number. You can move to slide number 17. You can make it full screen, sir, and move to slide number 17. Hello?
Yes, sir. 1 minute. We are trying, sir.
Okay.
1 minute.
Okay. Okay. Okay, sir. Okay. So can you make it full screen, sir? Then I will. Am I audible, sir?
Yes, sir, you are audible, sir.
Okay. So this is the solar radiation fundamentals that I was telling. So solar radiation and solar constant. This is I have told you about the solar irradiation and the solar constant. So the solar spectrum is on the right hand side. So ultraviolet spectrum, the visible spectrum, and the infrared spectrum. And from the different types of particular wavelength also it is given in the x-axis and the y-axis. You have the spectral irradiance. So the solar spectrum and the solar radiation fundamentals regarding the altitude and azimuth angle. So these are basically required, okay, for understanding of the solar research. Okay, so for solar research, you basically have to work on this particular areas. So on a very strong, so you have to have the idea of what is solar irradiance, what is the solar constant, and what is solar spectrum. Okay, what is the wavelength of infrared spectrum, ultraviolet, visible, like that. Okay. So next slide, please. Next slide. Hello. Next slide.
Please move to the next slide. Hello. Next
Next slide.
please.
Sir, actually, one person has to be deputed, otherwise it will move. Actually, I am not getting, sir. Actually.
Yes, sir.
So
Yes,
actually,
sir.
now the it is coming up. So let me start again. Actually, it is having some time. So I don't know whether they will allow me or not. So if it is there, then I will again start. Okay, from my end. Okay. So you can go to the next slide. For the time being, I will not waste further time. Can you go to the next slide, sir? This is not the next slide. The next slide is, this is slide number much. So go to slide number 18, 18. Yes, 180. Yes, this is the solar radiation. So the solar irradiance formula is, it is the power per unit area received from the sun in the form of electromagnetic radiation, right? So solar irradiation is the power per unit area received from the sun in form of the electromagnetic radiation in the wavelength range of the measuring instrument. So it is typically, you can see that is typically measured in watts per square meter and represents the solar energy reaching at a particular area on the Earth's surface. Next slide. Solar angle. Next slide is the solar angle. So basically in our research we required the understanding of the azimuthal angle and the altitude angle. So it is in the next slide. So this is the solar angle. Yes. So here you can see that this is the basically this is the solar angle slide. The azimuthal angle also you can see the angle from the sun and that is the normal to the Earth surface. Then also the altitude angle also you can see. So these two angles are very important for in PV SYST system of research. Okay, altitude and azimuth angle. Next slide. So what is the advantages of solar energy? This is the very basic slide. So next slide is the advantages of solar energy. So solar energy is abundant and will also not run out as long as the sun exists. Obviously, next quite million years, it will we can continue using the solar energy. Then it is reducing the electricity bills also. Using solar energy, we can significantly cut down or eliminate utility cost. The solar system requires minimal upkeep once installed. The environmental friendly also, it produces clean energy with no greenhouse gases. and also it is scalable, suitable for both small houses and large commercial installations and job creation. The solar industry supports many jobs in manufacturing, installation and maintenance, right? So these are the very important uses of solar energy. So the disadvantage is in the next slide. So obviously the installation of solar panels and related equipment can be very expensive. The weather dependent solar energy production drops on cloudy or the rainy days. So obviously you understand that when there is no sun, there will be no solar energy production. Energy storage is expensive. Batteries are storing solar energy are costly and have limited capacity. It requires a lot of space. So solar panels need significant roof or land space for large scale generation. Then inefficiency, solar panels typically convert around 15 to 22% of the sunlight into electricity. The manufacturing and disposing of the solar panels also create a lot of environmental pollution, and solar systems don't produce electricity after sunset without storage. Then there are some aesthetic concerns also. Some people find solar panels unattractive on buildings, location limitations, less effective in areas with low sunlight or long winters, maintenance needs. So there is a dust collection on the solar panels which require to be cleaned, and there is a regular inspection that you need to do. So all these issues are there on the disadvantages of the solar energy. Next, we'll come to what is a solar panel. So solar panels are commonly called, next slide, sir. Solar panels are commonly called photovoltaic. This is not the slide, sir. This slide. So solar panels are commonly called photovoltaic panels. So photo means light and voltaic means electricity. The photovoltaic panels are made from silicon, which is the same material that makes up the sand. So silicon is heated to extreme high temperatures at a factory and then formed into very thin layers. When the sunlight hits the PV panel, it moves around tiny particles of silicon called electrons. The silicon electrons then travel through the wires that are built inside the PV panels to create the energy. So it is not very straightforward, but this is how a solar panel is built. So these are basically made of silicon, which is heated to extreme high temperatures and then form into very thin layers. So when the sunlight hits this panel, it moves around the tiny particles of silicon called electrons. So these electrons are responsible for electricity that we all know. Okay, next slide. So how to use the solar energy, solar thermal energy. So solar radiation, yes, working fluid, solar collector, we get the solar thermal. So the solar radiation then we are receiving on the plate. So there is a lot of research going on in this particular area, the thermal energy and working fluid. So on the right hand side, you can see that one is red, another is blue. So blue is the cold water working fluid, and when the fluid it is coming out on the top portion, we can see that here we have the thermal energy is form of hot water. Okay. So then we go to some recent research paper highlights. The next slide. Okay, so CSP and thermal energy. So recent studies actually are exploring advanced receiver concepts for CSP systems. So CSP means this solar panel, this is focusing on liquid, gas and solid heat transfer media to improve efficiency. So CSP systems optimization research on honeycomb, volumetric and solar receivers highlight their potential for enhanced thermal and mechanical performance in CSP applications. Then hybrid CSP photovoltaic systems. These studies investigate solar tower competitiveness using the star-step receivers, aim to boost efficiencies and reduce cost. And there are also a lot of innovations on the solar thermal innovations. A special issue on solar thermal energy covers advancement in solar desalination and industrial heating and hybrid CSP PV systems. I have put this particular research papers in the slide. Anybody who is interested for doing research on these areas, this solar CSP and thermal energy storage, can refer to my particular PPT, where they will get access to this particular resource. Okay. Then PV SYST applications, recent papers also validate PV SYST's accuracy in forecasting solar energy performance, confirming its reliability for grid connected and off-grid
So
So can you listen to me, sir? Hello?
Yes, sir, you are audible, sir.
Okay. So then next slide is research gaps in CSP, PV, SYST and solar thermal. So high investment remains a barrier. Research on low cost materials and efficient thermal storage is needed. So limited studies on optimal integration combining CSP and PV technologies are actually there, and this is the research gaps where any researchers who is actually working on this particular areas of CSP, okay, PV, SYST or solar thermal can refer to these particular areas where there is more scope of publication and research. So, okay, so advancements in thermomechanical storage could enhance CSP reliability. So, regional climate adaptation studies on solar system performance under extreme weather conditions are also lacking. Okay. Building integrated photovoltaics. Okay. I'm not being able to understand. Hello.
Your audio is not clear, sir. So we are not
Hello.
able to hear you properly. Audio is not clear, sir. We cannot hear you properly.
Now it is audible, sir.
Yes, 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 sir.
And now is it audible, sir?
Yes, sometimes it's coming, it's breaking. Your voice is breaking. Sometimes it's coming clearly, but sometimes it's having some problem.
Actually, so I'm not on. Actually, internet connection is very much unstable, as I said. So that is the issue actually. Uh,
Yes, sir. You are now
did I share the
audible.
slide? Okay, yes, this is the slide. This is the slide. Okay, so this is the slide actually, as I was telling. So a lot of research which has already been done on the building integrated photovoltaics and the key considerations for building integrated photovoltaics are the panels should blend seamlessly with the building. Solar orientation and shading analysis, proper placement maximizes sunlight exposure, and BIPV panels can be tailored to in shape, sizes, color to fit different architectural styles. Right. হ্যাঁ 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 আমি তো আবার নতুন করে আবার ইয়ে করলাম আমি অন করছি হ্যাঁ নতুন করে অন করছি দেখি অন্য করে অন করছি আবার হ্যাঁ দেখি আমি আমার মোবাইল দিয়ে অন করছি ঠিক আছে
All the participants are requested to please be connected with us. There is a technical issues at the speaker's end. He'll be joining soon. All are requested to please be joined with us.
Yeah, am I audible?
Yes, sir,
Hello?
you are audible. You are
Am I
audible, sir.
audible?
Yes, sir. Yes, sir.
Yes, sir. So actually, can you go to the next slide? Modeling and simulation tools. Yes. So the solar panels is basically modeled in the MATLAB and Simulink program. In addition to governing mathematical equations, we are basically also doing a lot of research work using MATLAB, and COMSOL multiphysics is also used in solar energy research. And they are also used for modeling photovoltaic PV system, concentrated solar power means the CSP, and the thermal energy systems. Okay. And it is enabling multi-physics coupling, allowing researchers to analyze electrical, thermal, and optical interactions within solar devices. So someday if I get to visit your college in offline mode, then I can show you the researchers' research work that I have done on this particular COMSOL multiphysics using CSP technology. But due to the limitation of time, actually I cannot show you this particular research in the particular online mode, because there's a lot of issues which is coming up due to the internet. So that is a very big problem. So recent research on solar cell is also done by COMSOL, and efficient solar cell design is also being carried out by solar COMSOL multiphysics in solar mode. Okay, so these are the modeling and simulation tools basically we use in the research. There are other ANSYS tools also. ANSYS tools are also used in research in solar energy, but actually I have not explored the ANSYS one, so I cannot tell you more on that. But obviously I have done made a lot of research or published papers which is based on COMSOL research and PVSYST system, right? So this is the areas where I have mainly focused. Okay, so then you go to the next slide, sir. Okay, photovoltaic. So photovoltaic comes from the word photo, which is meaning light, and volt, a measurement of the electricity. And the photovoltaic electricity is obtained by using photovoltaic system. So the photovoltaic system consists of the four components. Here you can see from the figure right hand side, there is the solar panel, the battery, the regulator, and the load. Okay. Next slide. Solar panel. So solar panel is a indispensable component of the system that you can see from the previous slide. So solar panel is a part of the photovoltaic electricity, and solar panel is responsible to collect the solar radiations and they transform it into the electrical energy. And basically the solar panel is an array of the several solar cells, photovoltaic cell. These arrays can be found by connecting them in parallel or series depending on the energy required. Next slide. Yes, thank you so much. Solar panel manufacturing technology. The most common solar technology is crystalline Si, so silicon. It is two types are there, mono Si and the poly Si, right? The mono Si is the crystal lattice of the entire sample is continuous. So on the right hand side, you can see this is the mono Si, which it looks like. So it is the crystal lattice of the entire sample, which is a continuous figure. Here you can see. And the poly Si, it is composed of many crystallites of various size and orientation. So I will discuss about the advantages of this mono Si and poly Si in the next slides. Okay. So the next slide. Yes. The solar panel manufacturing technologies. The poly Si solar panel, it is composed of a number of different crystals fused together to make a single cell. And the poly Si panels have non-uniform texture due to the visible crystal grain present due to the manufacturing process, right? and the efficiency is around 14 to 16% for poly SI, and it is cost effective and is commonly available in the market. So on the right hand side, you can see the visible crystal grain in poly SI. Okay, so next slide. Okay, so this is the solar panel manufacturing technology. The disadvantages are not as efficient as mono SI. So mono SI is the most efficient part. There is a large amount of silicon and it is highly embodied energy. So visible difference between the mono SI and the poly SI panels. Okay, so on the top it is the black one is the mono SI panel, and on the bottom is the blue one is the poly SI panel. So mono SI color cells are of dark color, and the corners of the cells are usually missing, whereas poly SI panels are of dark or light blue color. Okay, the difference between the structure is only due to the manufacturing process. And the mono SI panel is basically the most efficient part. So go to the next slide, you can see the comparison. Yes, this is the comparison slide. So from the this comparison table, you can see that most efficient is the mono SI panels. It is the most efficient with maximum 21% efficiency. The poly SI panels is less efficient with around 16% efficiency, and the thin film panels is having the least efficiency with maximum efficiency ranging of 12% only, right? So the mono SI panels are manufactured from single SI crystal. The poly SI panels are manufactured by fusing different crystals of SI, and thin film panels are manufactured by depositing one or more layers of the PV material on the substrate. So basically, I am not going into the details of how there are different layers of PV material is produced or not, but you have to have an idea about this substrate, then PV material manufacturing, then mono SI, poly SI. Okay, so this is very important, and you must also have an idea about the different basically efficiency also. Okay, so if you are aware of the efficiency, then you can also carry on your research in the respective domain. Okay, and you can understand which gives you the more efficiency regarding the cost or watt per hour. Okay, so this is very important to understand which is having the cost, the least cost per watt. Okay, so the performance is based at the standard temperature for mono SI. The performance is based at moderately high temperature, and the performance is based at high temperatures for the thin film panel, right? So basically mono SI panels can perform at the standard temperature, means it is the normal temperature also, and this requires least area. Also the poly SI panels also require less area, but thin film panels require a large area for given power. So the mono SI panels have large amount of silicon, hence have high embodied energy, and also poly SI panels also have large amounts of silicon, but the thin film panels have low amount of silicon, hence low embodied energy, right? The performance degrades in low sunlight conditions for mono SI. The performance is less affected in low sunlight conditions for thin films. Okay, so if you are in an area where there is very, very less sunlight, okay, so you can proceed with thin film panels because the performance is less affected by the low sunlight conditions. From the cost per watt, you can picture, you can see that the cost is minimum for the thin film panels, right? Obviously, if the efficiency was, it is the least, and also the cost is also less. So if the cost is a hindrance, then you can proceed with the thin film panels, right? And the manufacturer, largest manufacturer for mono SI panel is again USA. For the poly SI panels, it is Suntech, and the thin film panels, it is the solar, is the China, US. Okay, so this is giving you a comparison of the mono SI, poly SI, and the thin film panel. Next slide. So how a panel is created? And so basically you can see that an individual PV cell typically produces around 0.6 watts and are joined in an array to produce the required power. Okay, so on the right hand side you can see the panel wiring diagram connecting the cells. Okay, so this is how basically a panel is created. A typically PV cell produces 0.6 watts of power and is joined in an array to produce the required power. Next slide. So what is blocking that? Okay, when the sun shines, as long as the voltage produced by the panels is greater than that of the battery, charging will take place, right? So, but when there is no sunshine, there is darkness or there is no light. Okay, when no voltage is being produced by the panel, the voltage of the battery would cause the current to flow in the opposite direction. Obviously, we do not need this. Okay. So what you need to do? So you have to block the diodes through the panels, which can lead to the so the battery will get discharged. But we do not require this. So what you do? So any electrical student who is at an electrical faculty or student who is attending the session can understand that by blocking the diode in series or panel, the battery will be in the reverse bias. Okay. And this is by way the current will not flow in the opposite direction. And the normal PN junction diodes can be used as the blocking diodes. Okay, to select a blocking diode, you follow the thing is have to be mind that of maximum current produced by the panels, the voltage rating of the diode, and the reverse breakdown of the diodes. So if you have an idea about this particular maximum current production, the voltage rating of the diode, the reverse breakdown, you can easily take care of the flow of the electricity in the opposite direction, which will not cause to flow in the opposite direction, and hence your basically the PV panels will be basically safe. Okay, so this is a very important way when you do this practical work with PV panels. You have to have this idea. Okay, how the blocking diodes are done, you can see on the right hand side panel. So this is by blocking diodes. Okay, so this is how we do that, right? So we have to have the idea of the current voltage rating and the reverse breakdown. Next slide. Solar panel specification. So the solar cell defines the types of modules or cell used in the module, the mono SI type, poly SI type, or thin film. Then the design implication means it determines the classes of conversion efficiency of the module. Then the cell dimension. Cell dimension means it defines the size of the cell used in the module. Okay. For example, 125 by 1. So that means it is 125 millimeter. Okay, that can be 5 inches. Then what is the design implication? The design implication means it determines the output power of the single solar cell. Then there are other definitions also, the mechanical specification, sorry. Then it is called the module dimension. This determines the size of the panel. Okay, design implication determine the number of cells accommodated in the module, the access length, the access breadth, number of cells. Okay, so these are standard formulas that you have to remember while you are working on the solar panels. Okay, next the electrical specification. Next slide. Okay, so the peak power defines the maximum power of the panel. Then the operating optimum voltage defines the highest operating voltage of the panel at the maximum power. The STC, okay, operating voltage. The design implication is determines the number of panels required in series. Then the optimum operating current. This defines the highest operating current of the panel and maximum power at STC. So when you are basically working on the solar panel, you have to idea of this mechanical specification and electrical specification, because when you are writing the research paper, basically you have to mention the mechanical specification clearly, otherwise your paper will be rejected. Okay, the mechanical specification and electrical specification. It is very straightforward because any person who is working in this area might be knowing. But obviously, when a person is new to this particular area, he might face a little bit of blockage. But these are very straightforward things that you can get in any textbook, okay, of this solar panel covering the areas of the solar panel, right? So not much to tell, but yes, obviously they are very important for understanding the solar panel. Okay, then the other electrical specifications are open circuit voltage, the short circuit current. Okay, then the design implication, this determines the current rating of the fuse which is used for protection. Okay, what is the conductor size, right? Then what is the maximum number of modules you require to be put in series? Okay, then what is the number of bypass diodes if you are using it? Okay, so as I already told you about the bypass diodes. Okay, the current rating of the fuse also. These are already been discussed. So from the curve you can see the current voltage where is the actually it is the drooping. Okay, so from the you can see the area general IV curve. Okay, so this where is the V operating and what is the V max. So V max is also given this particular by this point. Okay, this point is actually the black point. The black point on this curve, that is actually the corresponding to the V max. And on the right hand on the with the actually circular one, that is actually it is touching the x-axis in the voltage, that is the VOC operating OC, okay, open circuit voltage. So open circuit voltage and Vmax is very much important for electrical persons, but obviously any researchers who is working on this area must have an idea of the open circuit voltage and the voltage maximum voltage. Okay. Next slide. Electrical specification is again, there are some other electrical specifications also we need to discuss. This is the current and voltage variation for the panel, also shows the IV characteristics for different irradiance parameter. You already know the definition of irradiance. Okay. So the variation in IV characteristics with different amounts of watts. So upper one is a little bit, this figure is not very much clear. Okay. So I apologize for the same. It is not very much clear. So the top one is 1000 and the bottom is 800. So it is, and the bottom it is 200. So 200, 500, 700, 800, 1000. Okay. So the characteristics, IV characteristics, which determines the current and voltage variation for the panel. Okay. So the parameter determines the module current and the voltage for the particular case of irradiance. So this basically you can use to obtain the output voltage at the lowest irradiance for a given region. Next slide. So this is the comparison of the mono, poly and amorphous silicon solar panels. So you can see that the thin film ASI China solar, this is giving the optimum operating voltage of maximum, that is 18. The optimum operating current is basically for all the three, it is basically the same. You can see it is 0.285 for monocrystalline. For polycrystalline, it is 0.29, and for thin film, it is 0.278. Okay, the warranty is basically same also, and for 90% power output, warranty is 10 years for all the same. Okay, the maximum power at STC is also the same. Okay, so basically these parameters are not very much varying. Okay, only the open circuit voltage is little bit higher for the thin film, 26.7, and but for the monocrystalline and polycrystalline, it is the same, 21. Okay, and module efficiency also it is around 16% and 14% for monocrystalline and polycrystalline respectively. And the temperature coefficient we are not discussing, but I have put the values. The maximum system voltage is the maximum for monocrystalline, and it is lesser for polycrystalline and thin film. Okay, next slide. So now we'll go to solar cell. So the structure that converts the solar energy directly to DC electric energy, it is called a solar cell. So it supplies a voltage and current to a resistive load, light battery motor. So power is equal to current into voltage or current square into R or voltage square by R. So it is basically like a battery because we are supplying the DC power, and but obviously it is not a battery because the voltage supplied by the cell will change with changes in the resistance of the load. Okay, so you can say it is like, so on the right hand side you can see that one particular that I have encircled, this is actually is called a solar cell. On the topmost particular part of the slide, you can see that is a solar cell. So which converts solar energy directly to the DC electric energy. Next slide. So this is the silicon solar cell. Next slide. Okay. The operation of the photovoltaic cell requires three basic attributes. So you have to know this also, this theory. The absorption of the light in generating either electron hole pair of excitons, the separation of charge carriers of opposite types, the separate extraction of those carriers to the external circuit. So this is taken from the soft condensed material physics group. So basically when you are working on the PN junction diode, you have to have this knowledge about the absorption, separation and extraction. Okay. So the PV cells require these three particular attributes to the absorption of light, which is generating either electron hole pair or excitons, we say it in science, the separation of the charge which carries of opposite types, and the separate extraction of these carriers to the external circuit. Okay. So I will not discuss in details about this particular site. And this is the solar cell generations. You can see this figure categorizes solar cell into three generations. The first generation includes silicon based cells. Next slide. Next slide, sir. So the figure categorizes solar cells into three generations. The first generation includes silicon based cells, single crystal and polycrystalline. The second generation features thin film technologies like copper, indium, gallium disulfide or amorphous silicon. And the third generation explores advanced materials such as perovskite, organic dye sensitized and quantum dot solar cells, which is aiming for higher efficiency and flexibility. So here I put it in form of this particular solar cell generation. So anyone who is researching on the say third generation will be more acceptable because of the more research which is going on, especially on perovskite and organic dye sensitive third generation solar cell. Okay, so dye sensitive also is a lot of research is going on, and also the quantum dot solar also. Okay, so this I have taken from Sam et al. Research paper. Next slide. So photovoltaic solar technologies. So photons will strike the surface and emit electrons. As a result, electron hole pair is created in the solar cell. When external circuit is connected to the solar cell, electrons flows in the circuit and the current is generated. This is the basic technology of the photovoltaic solar. So can you, next slide, sit. So can you play this particular video, sir? Just you click on that. Is it playing? Okay, sir. Then leave it, sir. Go to the next slide, sir. Yes. So this is the difference between the grid connected and off-grid systems. The energy source, the features is energy source are divided into the grid connected PV systems and solar panels, the utility grid, and off-grid it is the solar panels plus battery. So in off-grid there will be battery. So the power backup, grid acts as the backup. So in case of off-grid, the batteries or generator is required. So excess energy handling, the excess that you are generating, it is directly exported to the grid. And for the off-grid system, it is stored in the batteries, or maybe it is wasted. So the inverter type is MPPT based grid inverters. So MPPT based charge collectors and standalone inverters is there for off-grid system. The PV's SYST simulations that we do for grid system, this actually covers for performance ratio, shading, loss diagram, economic analysis. And for off-grid, we basically do consumption profiles, battery sizing, state of charge trends. And for the system efficiency, it is high due to the grid support, and it is lower due to the battery losses. The best application for grid application is urban, industrial, large-scale projects. And for off-grid, it is remote agricultural standalone solutions. Energy reliability is very high due to the grid backup. And for off-grid, it is dependent on the battery capacity and sunlight availability. The economic feasibility is lower upfront cost, long-term financial autonomy is there. But obviously for off-grid, higher upfront cost due to the batteries, but long-term autonomy. So this is the basic difference between the grid connected and off-grid systems. Next slide. Okay, so the role of MPPT. So maximum power point tracking in PV SYST plays a crucial role in optimizing solar system efficiency. So inverters play a crucial role in solar PV systems by converting DC power from solar panels into AC power. So we have AI enhanced inverter, modern inverters integrated artificial intelligence for real-time optimization, improving efficiency, grid stability. Then there is hybrid inverters also, which is combining battery storage with solar inverters, enabling energy backup, grid independence. Then there is a lot of areas regarding the maximum power point tracking system in a PV versus SYST, where we have to do the dynamic adjustment for maximum power, the loss analysis, the energy yield estimation, the performance ratio improvement, the pumping system. So if you are working on the pump area, then MPPT stabilizes fluctuating solar irradiance, ensuring consistent motor operations. Okay. So this is about the MPPT and the power electronics. So you have to have this knowledge also for PV SYST system. So DC-DC converters in next slide, sir. Okay. So DC-DC converters plays a crucial role in solar power system, optimizing particularly in MPPT, maximum power point tracking. So how the DC-DC converters function? So PV SYST simulates step up or step down or DC converters for tracking the maximum power point of the solar panels. So grid connected and off-grid system converters optimize DC voltage levels before feeding energy into inverters for AC conversion. Then the loss analysis, the PV SYST calculates DC-DC conversion losses, including the heat dissipation and switching inefficiencies. Then the pumping application in solar water pumping, DC-DC converter stabilized voltage for efficient motor operation. Now the design optimization techniques. Next slide. So tilt angle. So tilt angle is the angle between the solar panel I have already discussed earlier in the previous slide. So the key consideration in PV-SYST is based on latitude, generally equal to the latitude for maximum year-round energy. So it depends on in which latitude you are working, right? So tilt angle is very important. You have to select the tilt angle properly. And there is fixed tilt versus tracking. So fixed panels have a set angle while trackers adjust dynamically. The PV-SYST allows simulations of single axis, dual axis trackers. So which is improving your output by 20% to 30%. And the optimal orientation also depends on the direction panels, which is basically typically south in northern hemisphere and north in southern hemisphere. Okay, the optimal orientation. So I am not going into the details of that, but I am actually urging you to little bit of research you must do on the optimal orientation regarding this particular direction panel and how you choose. Okay, and another important thing I also mentioned earlier, this azimuthal angle. Okay, so PV-SYST evaluates this azimuthal angle, minimizing the shading and optimizing exposure. Okay, so if you want to increase the efficiency or optimize the power output, then you have to work on this particular azimuthal angle, minimizing the shading and optimizing the exposure, right? Then the total capacity is needed based on the energy demand. So you have to first calculate the energy demand. Then you have to define the array capacity, the inverter selection, the battery sizing, right? So there are a lot of options which is there in the PV-SYST 3D shading models. But yes, obviously, these are not free software because you have to maybe 1 month facility will be given to you for the students. After that, you have to purchase this software. Okay. So if you want to work on the 3D shading models and tools like far shading, horizontal profile, near shading, then you have to work on the PV-SYST. Okay. The energy yield estimates also is very important. It forecasts systems for different setups. Next slide. Okay. So this is the performance ratio formula. The performance ratio is a very important matrix of the PV-SYST system, and this performance formula is calculated by actual energy output by expected energy output into 100%. So typically it must be not less than 70%, and it should not actually not go above 85%. If it is going above 85%, that means there is some error in your calculations. Okay, in the simulation. Okay, so you have to be careful. Okay, so you should basically rely between 70 to 85%, and this indicates better system performance considering losses due to shading, temperature, and inverter efficiencies. So there is another formula which is the capacity utilization factor. So this is basically the formula is actually calculated by actual energy generated in kilowatt hour divided by installed capacity per kilowatt hour times the hours in the period in 100%. So basically the CUF will range for 15 to 25% and is influenced by irradiance, system losses and downtime. And there will be some deficiency, also efficiency degradation in PV-SYST due to the dust accumulation, as I said earlier, light induced degradation, thermal stress, environmental exposure, okay, maybe due to the war situation, okay. So these force majeure conditions. So there will be some losses also in the efficiency degradation in PV-SYST system. In the environmental, next slide, sir. Okay. So the PV life cycle emissions in the PV-SY system can estimate the carbon footprint reduction. Basically, we are going to the carbon reduction scenario. Okay, so a lot of issues are there on the carbon reduction part and the Geneva Accord. Okay, so you have to reduce this carbon footprint and also the emissions. So typical emissions for solar PV system range from 25 to 50 gram of carbon dioxide per kilowatt hour, much lower than fossil fuels. Okay, so this is why we are more concentrating on the research on PV-SYST system, and includes manufacturing, transportation, installation, operation and end of life, disposal emissions, then land use considerations. Also, typically it is requiring not very large areas. So typically for large scale PV, you require 2 to 4 acres per megawatt. So you have the dual strategies also. You can use it both as agro voltage, means solar plus agriculture, then thereby you can minimize land competition. Okay, there is another option for recycling and disposal of solar panels also, because okay, so basically 25 to 30 hours is the PVSY, the solar panels have their lifespan. After that, basically you have to recycle them, otherwise you have to throw them. The key materials like silicon, glass, aluminum can be recovered and reused in panel in recycling. And emerging area research focuses on low cost recycling techniques and circular economy models for sustainable disposal. Next slide. Okay, so the financial models and LCOE. So LCOE is the levelized cost of energy. So the economic factors is the capital cost, the operational cost, the LOS LCOE. So this includes the solar panel inverter costing. Then it is how it is calculated, the upfront investment needed for system installation, the recurring expenses for system maintenance and repairs, then the total cost per unit of electricity generated over the system's lifespan. And finally, you also calculate the ROI, okay, return on investment. Basically, ROI is actually for any model. Okay, so any particular engineer who is working on the setup of this particular PVSY system must have an idea about the return on investment. Okay, so if you are not working on the return on investment, that means you are not a intelligent person. You may be called a foolish person, because you basically have to work on the profit. So PVSY system performance, cash flow analysis, payback period estimation, financial projections, these are also very much required. Okay, have to an idea about how this return on investment is basically calculated. And now due to the advent of ChatGPT and other AI tools, this is actually in a fraction you can basically calculate the economic viability of your system. Okay, and the levelized cost of energy, right? Now this is the second next slide, sir. So now we are the PVSY system is completed. Now we go to the concentrated solar technologies. So this is the solar technologies, the classification of the CSP system. Okay, the flat plate collectors, then solar technologies, the solar chimney, solar point. So for low temperature application, these are the CSP systems. And for medium temperature, we have the parabolic trough and Fresnel collectors. And for high temperature points, we have the central tower and the parabolic. Okay, next slide. Can you play this video, sir? If the video is running. If it is running, then you can play the video. Otherwise, you can exit and move to the next slide. Okay. Okay. So this is the parabolic trough collector. So the temperature is around 400 degrees centigrade. It is a line focusing method. It is a linear receiver tube. The water consuming, this is how the parabolic mirrors look like. The heat storage feasibility is there. This is most commercialized. It is good for hybrid operation, and it basically requires the flat light. Okay, next slide. Linear Fresnel reflector. Go to the next slide, sir. Okay. So linear Fresnel reflector, this is a very important research going on this particular linear Fresnel reflector. Okay. I was interested in this particular research, but due to the limited amount of time, okay, so I could not basically do this or present this particular research to you. But it is a type of concentrated solar power system that uses your long and flat, slightly curved concave or curved mirrors to focus sunlight into the fixed receiver position along the mirrors. So basically what you do here is to design track the sun along a single axis, right? Usually along the north-south, and is considered very cost effective, okay, and space efficient. Okay, the mirrors are basically flat or slightly curved, okay, and it reflects sunlight onto a common fixed receiver. And then you position the receiver above the mirrors, right? And it contains a fluid, okay, maybe it is the water or thermal oil or molten salt, okay. Then this gets heated up due to the concentrated sunlight, And the heated fluid is used to generate steam and drive the turbine for electricity generation. This is how the linear Fresnel deflector is basically we work on, right? Next slide. Okay. Central receiver tower. So this is the higher range for temperature, central receiver tower. So it is point focusing and it is flat concentrate mirror. So it is commercially proven to be very successful. And also the heat storage capability is also more. And it is also feasible on the flat slides and good performance for large capacity and high temperature application. So this I have calculated, taken the figure from the LCVR. Next slide. Okay, so this is the concept of the solar CSP technology. Okay, so reflector and concentrator, that is we receive the solar energy from the sun, then from the reflector and concentrator is the receiver and collector, then it goes to the storage tank and power, the power cycle or the engine interface, the power. So basically very simple, straightforward and a schematic diagram of how the CSP technology looks like. So solar energy to heat to electrical energy. So next slide, sir. So the CSP technologies are really very much means they are having very much future ahead. Okay, so this should be aggravated. Actually, parabolic dish technology for small scale power generation, then CRT, PTC, LFR. Okay, I have already discussed for large scale power generation, and a strong policy is also required by government. The solar fuel by concentrating solar radiation can also be adopted in the existing coal-based power plant. So CSP technology is actually lesser environmental impact, having lesser environmental impact, and this will actually increase the in the percentage electricity of what we generate by fossil fuels like coal. Okay, so we have to increase the CSP technologies. Okay, it should be aggravated for more power generation. Okay, next slide. Then I found that there are some very interesting trends in the solar research. So I have not done any research on that, but yes, obviously some new faculties who are more interested in doing research, they can work on this. I have mentioned some areas. You can work on tandem cells, bifacial modules, and AI-based optimization. Okay, so tandem solar cell is basically studying on perovskite silicon tandem cells, which is also, as I told you, very much in demand. Third generation. If you can go to the, if you can see, recall that previous slide, I told you about the third generation solar cell. So this is the tandem solar cell. Okay, so multi-junction solar cell combining 2 or more layers of different materials to enhance efficiency. And recent research is going on these tandem cells, which shows a 32.5% efficiency with optimization focused on band gap tuning and material stability, which is phenomenal. Okay, so 16-18% you are getting with mono SI PV cells, and here you are getting 32.5%, which is remarkable. So obviously these trends are very encouraging. Then there is bifacial solar modules. So solar panels that capture sunlight from both front and rear sides, increasing solar energy yield. This can also be, bi means both. Okay, bi means both. Bifacial means having 2 faces. Clear, very simple example definition. Bifacial tandems. This also shows quite high energy yield, 25% higher energy yield than a single junction of bifacial modules. Okay, so optimization focus will study rear irradiance, FACFX, module spacing. Okay, and they will optimize on the maximum efficiency. Then there is AI-based optimization in solar cells. By AI, you can actually, AI algorithms, you can enhance your solar panel efficiency. You can detect the faults, predictive maintenance. Okay, AI models can optimize the band gap selection, material thickness, real-time energy yields. A lot of applications you can do by solar forecasting, MPPT tracking, grid integration. Okay, so a lot of scope is there. Okay. So next slide. Role of AI and IoT. So real-time monitoring, AI analyzes historical data for predictive optimization, whereas IoT, Internet of Things, tracks real-time panel performance and weather. So many faculties or students are getting doesn't have a clear idea about what is AI and IoT in solar. So that's why I put a table to give you a brief understanding of what is the difference between AI contribution and IoT contribution, right?
So it is, there are different aspects you see. On the left, I have put the aspects, real-time monitoring. So AI will be focusing on the historical data for predictive optimization, and the IoT contribution is focusing on the real-time panel performance and weather. The predictive maintenance is on the area aspect. You can see the AI detects faults before they occur, and the IoT contribution is collecting failure data, enabling proactive alerts. The energy optimization, AI adjusts panel angles, then IoT communicates adjustments to devices. Then the fault detection and diagnosis is AI identifies anomalies, IoT sends alerts when performance issue arises. Then remote management and automation, here you can see the AI enables automated decision making for solar operation. The IoT cloud connectivity allows remote sense system control. Then the grid integration and forecasting, AI predicts energy demand and supply, improving grid stability. And then IoT collects consumption data to optimize energy allocation. Okay. Energy efficiency and sustainability, also AI refines solar system efficiency using machine learning, and the IoT ensures continuous monitoring for long-term sustainability. Okay, so there are 7 to 8 points aspects where AI is basically differing from IoT, and you can see that there is significantly different. So IoT is giving you real-time panel performance. Okay, and AI is only analyzing the historical data. So whatever is there in the internet, they are basically in ChatGPT. They will just calculate whatever data is available in the backup. But IoT is not like that. IoT will sense and track real-time panel performance and weather. So it is recommended to work with IoT rather than AI. Okay, from my side. Okay, the IoT cloud connectivity also allows remote system control. Okay, in the same, you can enable automated decision makings just as you can do in AI also. So if you can connect it cloud connectivity, then you can do work in both sense. Okay, so AI is refining the solar system efficiency using machine learning, whereas IoT ensures continuous monitoring for long-term success. So long-term sustainability is our main goal. So obviously, I will always go with IoT contribution, right? So the future prospects in Indian context is expansion of rooftop solar. Next slide, sir. Okay, future prospects. Okay, thank you, sir. So there are government initiatives like his PM Surya Ghar, Muft Bijli Yojana to install rooftop solar on 10 million homes. Okay, Modi Sarkar has introduced this. Then net metering policies encourage residential commercial adoption. Then for large scale solar parks and hybrid projects, okay, India is developing 40 gigawatt of solar and hybrid projects for 2023-24. So, okay, so I think this has already been met because we are now in 24-25 financial year. Obviously, this is the old data. And obviously, Gujarat is leading with 7,806 megawatt of solar powers using the 30 gigawatt hybrid renewable energy park. So next generation solar technologies, like as I said, bifacial solar panel, floating solar farms, AI-driven solar panel, okay, and IoT-related solar forecasting for better grid integration is recommended. Okay, so energy storage and grid modernization has to be improved. You have to build batteries which can stabilize intermittent solar power. Okay, so smart grids integrating the solar with AI-based demand and forecasting is the order of the day. And we should production link incentive scheme should be there for solar panel production. Okay, so this is very important that you have an idea about this solar panel production, solar park schemes for larger panels. Okay, next slide, sir. So the academic research opportunities in solar energy also I have mentioned some research areas for PhD studies in solar energy. So any interested faculty can look into this particular area if he or she is interested. They can work on research on perovskite, tandem and bifacial solar cells as I already discussed. So they can use machine learning for predictive solar energy modeling and grid integration. They can build areas, research work on building integrated photovoltaics, which is not being explored much in this particular context. Okay, urban solar absorption. Then they can work on the investigating battery technologies, battery technologies, thermal storage, and hybrid PV CSP, considered solar power systems, right? So some key funding agencies also I have mentioned, okay, which offers actually support regarding solar research in India. One is National Renewable Energy Fellowship for PhD and postdoctoral research. Then there is Bhaskara Advanced Solar Energy Based Scholarship, which supports PhD students and researchers for solar energy studies in India and the USA. Then Department of Solar Technology DST funds solar R&D projects through various schemes. This is quite difficult to get, but there are a lot of schemes are there for DST. Okay, Indo-US Science and Technology Forum is providing international research collaboration opportunities in solar. Okay. So this is the end of my first session. If you have any questions from this particular section, you can ask me, sir.
So thank you so much,
I
sir.
will take
It was
some
a-
5 minutes break, then I will go to the next, my next part. Any
Okay,
questions
sir.
from
So
part
if
one?
anyone having any question, so they can ask. From the audience, if anyone having any questions, they can type in chat box, or they can switch on their mic and ask.
Yes, sir. Thank you so much. I am very much thankful to you, sir. In the last moment, you have helped me a lot, sir, for
No, no,
carrying
sir.
out the session. I am really
Yes,
thankful to all of your
it
team, sir.
happens, sir. Thank you so much, sir. So anyone
Any
having any
questions you can
questions?
ask me, sir, because it was a long slide, but I will tell you to concentrate on the emerging trends in solar research. And basically, whatever I already discussed is the basics of the solar research. Little bit complicated, but CSP technologies are simpler to understand. Okay, especially the parabolic trough collector. And there are 2 videos also. I will tell the organizer to. I will share the videos by WhatsApp to the organizer. Okay, I will tell the video organizers to play these videos in the end. So to understand what is the PV SYST system working and how the CSP systems work. So okay, so I will share the videos by WhatsApp, because I put it in the slide, but it is not working. So I apologize for the same, but obviously I can obviously share these particular videos by WhatsApp to the organizers, and tell the organizers to share it to the to the interested persons who are interested for this research.
Sure, sir. Thank you so much, sir.
I will do it, sir. I will do it, sir. You tell me if there is any question, sir, from particular area, from this area. Okay.
Yes, sir. So if anyone having any question, they can ask. Please feel free to ask any questions from audience. They can type in chat box, or they can switch on their mic and ask if anyone having any questions.
Actually, it was a little bit, I actually moved very fast because of time constraint. But I actually wanted to cover everything of the major research areas of the solar. And now I will concentrate on the part 2. Okay, so I will not waste any further time, sir. Can you share the second slide, please, sir?
Yes, sir. Yes, sir. We are moving forward to the next slide.
Okay, sir. Sure, sir.
Yes.
Yes, sir. Thank you, sir. This one. Okay. So this is the part 2 of my research. So here I have actually presented 2 of my research works. One is the part 1 is the solar water pumping system design and analysis. This is a numerical study at Damdam, Kolkata. Okay, so next slide, sir. Okay. So this is the content is the abstract, introduction, methodology, system design parameters, simulation, conclusion, advantages, disadvantages, reference. Next slide. Abstract. So solar photovoltaic water pumping system is one of the best technologies that utilize the solar energy to pump water from deep well underground water sources and to provide
clean water for irrigation and drinking water worldwide. Okay, so India is a very now we cannot say that it is a developing country. It is already developed, and it has but obviously it has a very large population, and the total arable land in India is around 160 million hectares. Okay, so this is the old data. Obviously, now the arable land maybe has got increased. So according to the World Bank report, this was actually in 2022-23 when I did this work. Okay, it was around 35% of the total agricultural land was reliably irrigated in 2010. Okay, so you understand that there is a lot of emphasis that you can do by emphasizing the solar voltaic water pumping system. Okay, so the abundant solar energy resource and groundwater availability in India can be combined to make much needed potable water availability in remote areas of the country. So this research work is basically dealing with the design and technical analysis of the photovoltaic water pumping system for irrigation and fresh drinking water supply. Next slide. Okay. So this is the same as basically the previous slide. As I said, that given the world population growth, freshwater availability for 2050 is estimated to be 4,380 meter cube per person per year. So that's why by 2025, 3 billion people are only in the water stressed countries, and by 2050 we will be having very water shortage. So irrigated agriculture has to be increased. Okay, so irrigated agriculture by solar system, PV-SY system has a very high potential of research, and this is by which we can increase the total the production of the agriculture. Okay, so how you do that? So next slide. So several rural areas of West Bengal are currently suffering from acute power crisis because of recent cyclones. Okay, then non-renewable energy sources are the main energy sources of India, and the power generation sector is also heavily dependent on that. And obviously you can see the prices of fossil fuel and pollution levels are very much increasing. And okay, so the per unit cost of electricity is ₹7. Okay, but here if you can use the solar energy, your cost will basically go down. Okay, so it is having a lot of scope for this PV system. So the irrigation system comprises the PV array and pumping components such as the motor, then the positive displacement pump and a control system. So our aim is to design and optimize solar water pumping system and analyze its performance in PV-SY system software for irrigation purpose. Okay, next slide, sir. So here you can see the solar pumping system that we have used, the figure number 1, deep well solar water pumping system. The solar arrays, this is connected to the solar pump inverter. So it is pumping water and we are storing it in the water tank. The only requirement here is actually the solar arrays. So we are not using any electrical sources. So solar panels from their charge controller, the battery on the right hand side you can see the battery is optional. Okay. Then the solar pump inverter, then water pump, then the storage tank and distribution system. So this is how actually the system methodology works, solar pumping system, right, sir? Next slide. Okay, so MPPT AC inverter, as I already told about the maximum power tracker AC inverter is used for this power conditioning of the system. As I already told in the previous slides, in the basic slides. So PV-SYST 6.88 model was used to simulate the solar photovoltaic water pumping system. For 2 heads, we actually carried out a comparative study for 40 meter and 60 meter. So the inputs of the software that we have given to PV-SYST was the average solar irradiation, average daily water demand, well depth characteristics, selection of the PV modules, and the pump selection. Okay. So in the PV-SYST system, actually, I have shared the video to the organizers, sir. You can put on the video and share the videos to the organizers and to the faculty participants also, so that if somebody is interested for this research on PV-SYST, they can actually learn more on this video, from the video also. Okay, so this is a basically YouTube video I have downloaded, but this is a very simple video and tell you about how the PV-SYST
system works. I have shared the video, sir. Okay. So you can share it to the resource persons, having full support from the resource person, and you can also share it to the your organizing authority, and also to the this faculty who is participating in this particular solar energy research this activity. The final relevant results include the water delivered to the users, the excess unused PV energy, and the system efficiency during the year. So after running the simulation for the selected sites, we found the results. Now you can go to the next slide. Sir, actually, just 1 minute, sir. So this is the result. So this is basically the validation. I have first done the validation. So this was the validation study. So this is validation was done from another research paper called Tohari et al. We are validating the performance ratio, then the normalized production and the losses. So this A, B, and C is called the normalized production, then the performance ratio, and C is the loss diagram. So these three figures are basically validated from Tohari et al. Paper. And next slide, sir. So this is the system design parameter simulation. So this is the location of our Dum area location. So you can see the solar radiation data of the site. So for all the months it is given from January to December, actually it is given. Okay, so this is the definition of the geological site. Okay, so we had carried out this research in 2021. Okay, so I have published this in a Springer book chapter. So this is the project location. So go report Dum, latitude this, longitude this, baseline. So this is the number of global monthly meteor data. And this is actually, we can obtain it from the PBSYST system, the solar radiation data of the site. Okay, the solar parts. In the yellow, and the bottom portion, in the yellow portion, this is called the solar parts. Okay, the solar parts means that's how the solar actually travels. Solar actually system travels in the different months from January to December, right? Next slide. Okay, so this is the simulation input parameters. So during the design and simulation process of the system, it is assumed that the solar panels are not shaded. So we have not actually gone in for shading option. We have just made it non-shading option with a free horizon, and simulations are performed based on the maximum possible water annual water demand. The main design and simulation parameters are listed in this table 1. So this is the table 1, and next slide. This is table 1 is water requirement is 1,200 meter cube, and this is the table 2. Okay, so can you move to the previous slide? Yes, sir. Thank you, sir. So this is the water requirement 1,200 meter cube per day. Total head is 47 meter. The water storage tank volume is 240 meter cube. The well depth is 40 meter. Then the borehole diameter is 40 centimeter. Pipe length is 50 meter. Summer tilt angle is 22 degree. We have chosen in the PBSYST system. The winter tilt was chosen as 42 degree system. The azimuthal angle chosen was 0 degree. The solar panel type we had chosen is Trina solar. Model is a silicon poly manufacturer. So we have chosen the poly manufacturer, not the mono one. Okay, the pump type we have chosen is the actually the Grand Fox, the German pump. Model is SP 95.7, 37 kilowatt pump. Okay, the control device is the AMTTP AC inverter. Manufacturing is ABB, Asia Brown Boveri. So this is the design and simulation parameters. Next, you go to the next slide. Okay, sir. So this is the table 2 simulation parameters. So this is the again the water requirement we have kept it at the same. Okay, the solar panel pump type solar control device is also the same. The water storage volume well depth is however different. The pipe length is also different. Summer tilt and winter tilt is also made the same. Okay. So next slide, sir. Okay. So this is the simulation result we have obtained. So simulation for the 40 millimeter deep well, That is, we have got the simulation from the PBSYS system. Water pump is 23,000, 2,37,423 square meter cube. Water needs is 4,38,000 meter cube. Energy at pump is 4,48,075, 44,875 kilowatt hour. Then unused PV energy tank full is 3,60,075 kilowatt. The system efficiency is 52.4%. Quite not very high, but again not very less also. The missing water is 45.8. The unused fraction is 42.1, and the pump efficiency is 69.2%. Okay, so table next to go to next slide, sir. Next slide, sir. Next slide. This is for 60 millimeter. Is it for 60 millimeter? Next slide, sir. 60, yes. So this is the 60 table number 4. Table number 4, simulation result for 60 millimeter deep well. Yes, sir. Table number 3 and 4, this is the simulation results for previous parameters, which indicate the selected PV size. Here also you can see the water pump is 2,05,493 meter cube. Then water needs is 4,38,000 meter cube. Energy at pump is 56,217 kilowatt hour. Unused PV energy is 20,154. Here the system efficiency there is more than the 40 meter deep well. Okay, the missing water is also less, the unused fraction is also less, and the pump efficiency is also more. Okay, so this is very important. So here we have got the system efficiency for 40 meter as 52.4, whereas system efficiency for 60 meter deep well you have got 65.6, which is much higher. Okay, but the pump efficiency is more for 40 meter deep well. Obviously, it will be lesser, more for 40 meter compared to 60 meter. It is quite understandable because we are drilling more. Okay, the system efficiency is, however, more for 60 meter deep well. Okay, and the unused fraction is also reduced much in 60 meter case. It is only 23.5, whereas it is 42.1 in case of 40 meter. Okay, next slide, sir. So this is the energy balance of the solar pumping system. You can see I have put the this particular the parameters which we use in the PBSYS system: the unused energy, the collection loss, the system losses. This is the normalized productions per installed kilowatt hour. Nominal power is 54.0 kilowatt hour. So unused energy is 2.27. Collection losses is 0.42, and system losses is 0.19, and the effective energy at pump is 2.28, right? And here you can see the month of April, the energy is maximum. So from the fourth bar diagram, fourth one, it is the maximum in April, and then in May it has gone down, and it is the least in, I think, July and September. Again, it has got increased in October and November. Okay. So this is the trend for energy balance of the solar water pumping system. Next slide, sir. So this is the energy result. So I have put the legends also. The global efficiency is the effective global ER is the array virtual energy at MPP. Then the pump operation energy, the unused energy, the pump head, H is the pump head, average total head. The W pump is the water pump, then W used is the water drawn by user. So these are the different values of global energy, then pump head, then water pump, okay, for the different months. And altogether cumulative also, we have put the values, okay. So this is the total value of H pump meter is 47.68, and global efficiency in kilowatt hour is 1829, right? So these are the values cumulatively you have obtained. Next slide, sir. Okay, so this is for the other one, for the 40 meter. This is the 60 meter. Okay, so you can go to next slide. Next slide, sir. This is for the 60 meter. Okay, the same thing. You have I also plotted the table for global efficiency. So in that particular slide, we have got the global efficiency for 40 meter to be 1829.1, and here also we have got the same, but obviously the values have got changed for ER, so array virtual energy at MPP, right? Okay, go to next slide, sir. I have explained the slide. So figure 3 and 4 and table number 5 and 6 are the energy balance for the PVS system. It shows the normalized values for effective energy at pump collection losses and unused energy in the system. As you can see that the unused energy of the system is not low, and the system and the collection losses seem a bit higher. Okay, why is it bit higher? Is because the system is designed to pump the maximum possible of water per day using all available energy on the system. That's why the collection loss seems to be higher. When the production is maximizing subject to higher losses, if you reduce the amount of water pumped by the system per product. That's why you can see for 40 meter, we can see the losses are less. Okay. So if you can minimize the losses, the unused energy of the system will be maximized. So this is our observation. Next slide, sir. So this is the detailed simulation results for 60 millimeter deep well. I have put the values. You can see pumped water, water need, total water. So these are the values of the different values. The values: pumped water, water need, pump energy used, PV system underutilized. What is the underutilized? Also the excess energy that was not utilized effectively, and the water pumping ratio you can see in the last is 46.09, and on on a little bit higher you can see the performance ratio. So these values are actually very important, and it is the actually gives you the actual energy output to the theoretical energy potential, or maybe you can from here you can also calculate the losses also, the energy loss within the photovoltaic system. So basically our aim will be to decrease the losses, right? So if you can decrease the losses, then we can actually increase the performance ratio, and we can also increase the head loss, inverter loss, and unused fraction, and thereby increase the pump efficiency. So here you can see the system efficiency is 65.6 and the pump efficiency is 67.7. So conversion efficiency of the pump in delivering water, right? Next slide. So this is the monthly solar irradiation trends to analyze solar seasonal peaks and dips affecting system. So you can see, obviously, as I already told you, the March, April, May month, it is the maximum irradiance that we are getting, and you can that I have plotted in the graph so that you can understand it better. Same thing. Next, sir. So this is the correlation between the system efficiency and the array losses. So there also you can understand the system efficiency as the corresponding to 11.50 array losses. We are getting the system efficiency to be 15.4. So if you go to the left hand side of this particular graph, so that from there you can see that when the array losses are 11.5, then the system efficiency is 15.4. And when the array losses are basically 13, when you go to the right hand side of this particular table, the graph figure, you can see that the system efficiency is going down. Obviously, vice versa. So this is the correlation between the system efficiency and the array loss. It's very easy to understand. Somewhat will a little bit of intellect can easily understand the correlation between the system efficiency and array loss. So it is inversely proportional. So if the array losses are less, the system efficiency will be more. If the array losses are more, the system efficiency will be less. That's all. So this is the scatter plot which compares system efficiency versus the array losses. So how the system losses affect the performance. Next slide, sir. So next slide, sir. Yes, okay, thank you. Energy utilization trends for water pumping versus total PV energy. So the blue system is giving you the total PV energy, and the yellow is giving you the pump energy use. So from here, you can get the data for all the months from January to December. So this is the bar chart, which is comparing the monthly pumped water energy versus the total energy availability to check system efficiency. Next, So now I have put it the performance summary across the months. Here you can see that unused solar energy is actually varying, but the pump efficiency and the performance ratio is remaining the same. So overall for the year, we are getting the pump efficiency to be 67.7 and the performance ratio is 55. And the total unused solar energy from January to December is 36,075 kilowatt hour. Next slide, sir. Okay, so now you do some basically a financial analysis. We try to calculate the system cost. So suppose the solar panel 10 kilowatt is costing 5 lakh rupees. The MPPT inverter is costing 1,50,000. Then water pumping and controller is costing 1,20,000. The installation and miscellaneous cost is costing 80,000. So the total initial investment that you are doing maybe is 8,50,000. So if you want to calculate the break-even analysis, you can see that the break-even point is 13 years. So after 13 years, you will earn profit. So this is our cumulative savings into initial investment area, which gives you the area of the break-even point. So it's very important you calculate the estimated system cost and the break-even analysis. Okay. So that means after 13 years, you will earn profit. Next, sir. This is also very important how the energy is comparing solar versus diesel pump. Here you can see the solar pumping cost is much lesser. Okay, so it is much lesser. Cumulative cost is very less compared to the diesel pumping cost. So whenever you go into the agricultural areas, agricultural fields, you can see the diesel pump is working. But yes, in the near future, I think the diesel pump will stop working and will concentrate more on the solar areas. Okay, so here from the extracted annual savings, you can see that net savings per year is around 65,000. Okay, so it is very huge. So for 10 years or 15 years, this is phenomenal. So you are saving around 6,50,000 or 7 lakh amount. Okay, so it is quite a significant amount. So by removing the diesel pumping cost and promoting solar, you are actually saving a lot amount of money. So this type of graphs actually is required for this research. Otherwise, next slide, sir. So this is the ROI, okay, as I said, return on investment. So here you can see the ROI growth, the investment recovery. Okay, so a positive ROI indicates strong financial feasibility, and here we have got a positive ROI. Okay, so the ROI percentage is calculated by annual savings into lifetime minus investment divided by investment into 100. And here we have calculated to be around as 52.9%. So by 12.5 years or 13 years, you can say the entire recovery will be done. Entire recovery, and you will start earning profits. Okay, so this is next slide, sir. So break-even time, as I told, is around 13 years, after which savings will accumulate rapidly. Solar pumping is more cost-effective than diesel alternatives in long-term use. So potential for improvement, better utilization of unused solar energy could further increase our returns. So this is how we have calculated the levelized cost of energy, LCOE, that we have already discussed in the previous slide. Okay, so net present value also I have calculated. The payback period I have calculated. Okay. So these are the advantages. Solar I have already discussed, nothing more. Next slide, sir. Next slide. These are the disadvantages. In cloudy or rainy days, there will be no power. Water quality will not be that pure, need a lot of space. So global irradiance loss also have calculated. Array loss, inverter loss, system efficiency loss. These losses also is actually in the disadvantages. So this is the part 1 conclusion. The array losses are significant. Next slide, sir. So significant, suggesting optimization in parallel low output system design could improve efficiency. Inverter loss is 3.21%, relatively low, but still contributes to reduced overall performance. The final system efficiency is 15.22, which can be increased by reducing the error losses. So these are the references. I have published one conference paper and one Springer book chapter from this particular research. This was published in 2022. Okay. So can you go to the next part 2? Next slide. Yes. So this is the very recent work I have done. So this was published yesterday in a national conference. Both these works actually has been done by my undergraduate student. One was from Elite College of Engineering, and this was done from presently a fourth year student from Molandigi, Sonoka Educational Trust. So this is the smart solar forecasting using PV-SYS system. This is a normal case study in Molandigi. This is not among the pump here. So you can go to the next slide. So this study designs and simulates a solar power system for Molandigi villages using PV-SYS software to meet essential rural needs like lighting, water pumping, agricultural. Okay. So it evaluates the energy yield, performance ratio, efficiency, economic feasibility, and it's aiming to optimize the renewable energy adoption for sustainability, rural development. Okay, so here I have actually omitted the mathematical slides. Mathematical slides are also there, and when you are writing on the paper, you have to include the mathematical details about this PV-SYS system in details. Otherwise, your paper will not be accepted. Okay, so just I have to make it more easier to understand and simplify. I have not mentioned the mathematical analysis, but my request is that when you are writing such research and you are publishing, you have to mention the mathematical details, okay, of this particular research in PV-SYS. Okay, so this is the system details. So annual energy 45.1 kilowatt grid connected PV-SYS system. The annual energy production is 59,810 kilowatt hour with a performance ratio of quite high, 81.77%. The loss analysis, as we had found, is 3%, which can be mitigated, means can be reduced through regular cleaning. Okay, the thermal losses is 6.7%. Passive cooling strategies recommended. Light induced degradation is 2%. Optimized panel maintenance suggested. The seasonal performance peak generation is April-May. Again, it is similar for, as we have seen in case of water pumping also, with minor declines in monsoon months. The economic feasibility also, we have seen it is 13 years. So ROI is coming to be 52.9%. The solar system proves cost effective compared to diesel water pumping. Next slide. So this is the site location, Molandigi, how it looks like in the map of the PV-SYS system. So the green ones you can see, these are the agricultural fields actually, basically. It is a village area. So Kaksa area, you can see country, latitude, longitude, altitude, wind speed, everything is given. So this is how a site location is actually seen in a PV-SYS system. Next one. Next slide, sir. So why you have chosen Molandigi? Which is located at latitude 23.55. The optimal tilt angle for solar panels can be estimated as follows. So around 23.5 degree. So the winter is around 38.5. So summer is around 8.5. So seasonal adjustment. So it varies between 8 to 38 degree based on seasonal sun position and dynamically adjusts for maximum efficiency for dual axis tracking. So that's why we have chosen Molandigi, latitude 23.55 degree, latitude east. Okay. Next slide, sir. So this is the monthly weather data for Molandigi area. You can see the global horizontal irradiation, kilowatt hour per meter square, the diffuse irradiation, the ambient temperature, wind velocity. Okay, the wind velocity is not significant. Only in the month of June, I think it is crossing 3.5. Otherwise, it is all in the range of 2.1, 2.3, 2.6. Okay, so wind also, so wind velocity also, future also not very good, but yes, solar research is very promising in our area because the wind velocity is not very high, you can see. So solar research is quite promising in this area. So that's why you have, we try to do some solar research in Molandigi area by using this PV-SYS system. So here you can see the monthly weather data for Molandigi from January to month of December. This is for 2024. Okay, so 24 data we have calculated from the PV-SYS system. Next slide, sir. This is the high resolution sun path diagram. So here you can see the solar altitude. So on the left it is the solar altitude, on the right is the azimuthal angle, the azimuth angle also it is mentioned from minus 70 to plus 100. Okay, how it is varying actually the solar altitude. Okay, so you have to understand the sun path diagram for Molandigi. Any area when you are doing, you have to understand how the solar actually path crisscrosses at different solar altitude and occur at different azimuth angle. Okay, so here you can see 1, 2, 4, 5, 6. Okay, so which day the solar altitude is more and which day the altitude is late also. From there also you can see. So the solar altitude it is more on June 21. Obviously on the month of June 21 is the highest. After that is June 23. Then it is June 21. Then September. Okay, like that. So okay, so for the period of 4 or 5 years it is calculated. So here also from the left hand side you can also see that December 21 it is the lesser. So 6. So December 21 on the left. Okay, so these are the solar altitude paths and higher sun path diagram for Molandigi for from the year 2021 to 2023. Next slide, sir. So this is the methodology for PV SYSC system for this particular work. So we define the project, we put the meteor data, we choose the azimuthal angle, then we choose the plane orientation, and then we finally choose the PV array. And this is a grid connected system of study. So solar panel for our particular case, we have chosen a inclination angle to be 20 degree. We had used DC-DC converter, then the MPPT converter controller, sorry. Then from the grid, then this is converting DC to AC. So this is how the grid connected system methodology for PV SYSC simulation is undertaken. I have already discussed about the DC-DC converter, MPPT controller, DC-DC converter, inverter, AC to AC. All these things I have already discussed in the previous slide. Okay, so if you have actually, so that's why I wanted that the faculty should ask me questions on particular this. But okay, I didn't get any questions. But these are the areas actually you need to know. Actually, these areas actually you must have a good amount of mastery before you can proceed in this type of research. Next slide, sir. So this is the facility of the PV SYSC system. So it includes 3D shading analysis. Then software provides a vast meteorological database. Results are presented as detailed report with graphs and tables covering energy, loss analysis, performance validation. You can go to the next slide, sir. So this is the actually the validation study. So validation was done from, you have put it in the red box, a reference for validation. So this validates PV SYSC's accuracy in forecasting the solar energy for 45.1 kilowatt kWp grid connected system in Molandigi, comparing simulated results with historical data and industry benchmarks, that it ensures reliable rural site assessment. Okay, so it is matching with the reported yield, and performance ratio is quite significant. According to here, we have obtained 1325, and the ISC standard is 1300 to 1350. So it is quite phenomenal. It is very similar, okay, to the amount of area PV SYSC simulation that we have done. The performance ratio we have obtained as 81.77, and as the industry benchmark is 80 to 83. Again, it is quite significant. Okay, the empirical study also gives the value as 1275. So actually, you can see that PV SYSC actually is giving a little bit inflated values compared to the empirical study with PV systems. Okay, but it is very much you can basically compare the results, okay, with the industry standard empirical studies. Next slide. Methodology simulation data is modeled on a fixed span system with a DC-AC ratio of 1.3. The validation ratio is industry standard. Comparison matrix, energy yield, performance ratio, PR, loss factors, energy yield, validation. The simulation annual energy yield is actually 59,810 kilowatt. This is aligning with the expected values. And the loss analysis validation also we have not given in the table, but here I have put it is actually also matching to significantly It includes the soiling losses, the LID losses, and the temperature losses. Aligns with the industry benchmark that we have also put it in the reference. The thermal losses were particularly evident in the peak summer months. Okay. So next slide, sir. So this is the normalized production and performance ratio values, simulation results that we obtained for Molandigi area. So this is the normalized projects productions per install KWP performance ratio. It is 81.8. So you can see all the year round it is not very much varying, but yes, in Dom area performance ratio is bit varying. Okay, so this is the collection losses, the system losses, and normalized production. So get an idea about it is a quite a high food system efficiency and minimal losses beyond unavoidable external factors. Okay, next slide, sir. So this is the monthly variation energy peaks in April, May, while June through August shows a slight dip likely due to increased cloud cover and monsoonal effects. Otherwise, the temperature and irradiance is more or less same. The performance ratio, as I already calculated, 81.88%. So this is the monthly variation, losses diagram, temperature, irradiance, and energy yield versus performance ratio in a nutshell. Next slide, sir. Losses and efficiency factors. So this is the soiling losses I already discussed, mismatch loss, DC wiring loss, soiling loss. So this also you have to mention. Loss analysis, efficiency breakdown of PBSYST performance. Next slide. This is the weather data simulation parameter, uncertainties and probability distribution, average ambient temperature of 26.5 degrees centigrade. Considering that, it influences the thermal losses of around 6 to 7%. Right. So we can basically reduce the module efficiency. Okay. And solar irradiation, the total global horizontal irradiation is 1542 kilowatt per meter square, with around 921 kilowatt per meter square being diffuse radiation, implying some degree of scattered light. Okay. Next slide, sir. So this is the Molandigi site summary in a nutshell. So annual energy yield 59,810. Then the energy yield, the system production performance ratio, then specific yield, everything has been mentioned. Next slide. So the last part of this particular slide is the economic feasibility analysis. Here also you can see the cumulative cash flow. Okay. So cumulative cash flow for what 25 years, 45.1 kilowatt P system. It is around after 13.5 years, basically we are actually getting the annual return on investment 19.45% post to payback. Okay, so the cumulative cash flow over 25 years, net cash flow projections for 45.1 AWP solar PV system, 2.03 lakhs per year savings. Okay, so this is quite significant. So the red line, this is the red line where you can actually the initial years that you have to actually basically spend. Okay, the payback point is 4.85 years. After that, you have the cumulative cash flow. Okay, so up to 5 years, you have to basically invest, but beyond 5 years, your profit is just skyrocketing. You can say the skyrocket. Okay, next slide. So this is the total economic summary. System size 45.1 kWp, installation cost is 2,29,500, annual energy yield 59,000. Electricity rate prevalent in West Bengal is ₹7 per kilowatt hour. Annual savings is 4,18,670. Payback period is 4.87 years. After that, you will get profit. Annual return of interest, which is phenomenal, 19.45%. So it is huge. So it is just like investing in a mutual fund. So cumulative net savings after 25 years, your is 84,33,250. So imagine how much of amount you can save. Okay, the system reaches its payback point at approximately 4.87 years, after which it consistently generates positive cash flow. So over a 25-year period, this translates into a substantial net savings. The project delivers a stable annual ROI of approximately 19.45, indicating a strong and sustainable return on the initial investment. Okay. So next slide. So this is the conclusion slide. So the PV SYST simulation results for 45.1 kilowatt kWp grid connected solar system in Molandegi demonstrates a high efficiency performance with an annual energy yield of 59,810 kilowatt and performance ratio of 8.77, 81.77%. The research analysis confirms that solar project offers a quick payback. The system achieves a payback of approximate 4.87, means 5 years, after which it consistently delivers positive cash flow. So this was the published in national level conference on mathematics, pure applied mathematics, NCPAC 25, very researchful. Next slide. So this is the selective reference. Next slide, sir. This is the selective reference I have used. Okay, so number 4 is my paper. This is the Dom paper which got published in 2021. It was published in one conference, and then it came out in form of a book chapter in Springer Nature Singapore in 2022. So this was one of my student, Arnab Roy, who has done this work. And this Molandigi work is again done by one of my students named Sudarshan. He has done all the primary work, and I am very much grateful to both of my students. They are responsible for giving me these results. On their results, actually, I have made this PPT. So I am thankful very much to them. And this is the end of my presentation. And thank you for bearing with me for such a long time. And any relevant questions are with us.
Thank you so much, sir. So anyone having any question can ask.
If there is any question, sir, I will be very happy to answer those.
Yes, sir. So anyone from the audience, if have any questions, they can switch off their mic and they can
Yes.
ask.
Hello.
Yes, sir.
Yes. So my specific question is the main problem. One of the main problem. There are several problems with solar energy. Is that in stormy or rainy weathers, the solar energy is not available. And
Yes, sir.
second problem is the storage of solar energy produced. Okay, the electricity produced from solar energy needs to be stored in large capacity batteries. Okay.
Yes,
which
sir.
elevates the cost,
Cost.
isn't it?
Yes, sir.
So, any idea how it can be mitigated?
Sir, actually, basically, I told you that when we are actually storing the energy, so we have to consider battery. So we have to basically go in for research of this particular battery. So if you have a very good battery source where you can store this energy, and if this battery cost can be brought down, so I think in that sense you can actually basically reduce the cost, sir.
Thank you.
Thank you so much, sir. So if anyone having any more questions, please ask, as we are not having much more time. So we'll proceed further for the next session. If anyone having any question, please ask. We don't have much time left. Okay, so we'll proceed now for the next session. Kindly requesting Rahul for kindly close that PPT, and as we will be sharing. And now,
Thank you, sir. Thank you, sir.
As we conclude today's session, we extend our heartfelt thanks to Dr. Shantanu Datta sir for sharing his deep insights on solar energy technologies and their real-world application. Your expertise in depth knowledge have certainly enriched our understanding of the evolving landscape of solar energy. Now,
actually, sir, I very much apologize to Professor Bosak that I could not share it from my end. And actually, I am very much thankful to organizing authority for helping me. So I am very much thankful because of this erratic power system in our college. So I am very much thankful to the authority for helping me, rendering the help, and for continuously listening to my whenever I am telling to change the slide, you have changed it. So I am very much thankful, sir.
No, no, sir. Thank you very much, sir. It may happen. Network issue may happen anywhere.
Yes, sir.
So that's
Actually,
not
I'm.
a. Yes, sir. Yes,
So
sir.
that is the reason I told Sir Professor Bosak to make it. And actually, sir, I have told shared the videos also. So I actually tell you to basically share it to all the organizing committee and also the participants, especially the participants, because they doesn't have much idea about the CSP. So CSP technology is very new, sir. CSP is concentrated solar power and the PPSYST system. This is basically I worked it under when I was working under Professor Bosak itself in Elite College. That was the first time I actually came to know about PPSYST system. But solar concentrated solar power is again very, very new. So these technologies are very new, and actually I urge the students to do research on these particular areas, as I already mentioned. So there are several areas where these particular students can, or the faculties who are yet to do their PhDs, sir, they can actually do that. So I have shared the insights on these PPTs. Okay. So here they can actually do the work on these particular areas. Okay. So the videos of the concentrated solar power and the PBSY system I have shared, sir. Kindly share it to the faculty. Thank you.
Sure, sir. Sure, sir. Thank you so much, sir. We'll share it to the participants.
Thank you.
And
Thank you.
as we can see in the screen, a certificate of appreciation is presented to Dr. Shantanu Datta, sir.
Thank you, sir.
Kindly.
Thank you so much.
Thank you so much, sir. And a big thank you to all participants for their active involvement. And we
Yes.
look forward to seeing you tomorrow on 16th May, day 4 of FDP. The session will be conducted online and will feature the expert talk by Dr. Tado Gadi on bio-waste to energy, sustainable management of organic matter for renewable energy generation from 2:30 p.m. Thank you once again and have a wonderful evening ahead. And a feedback link will be shared to the chat box as well as the WhatsApp group. Kindly fill up the feedback form for getting the certificate. Thank you all. Thank you so much. See you soon. Goodbye.